Professor Clements with you as we again consider wave optics, interference and diffraction, and discuss how light interacts with small objects, small openings. So we've already covered the double slit. Our work continues here with the element called the diffraction grating. This again is in OpenStax College Physics in Chapter 27, I believe we're in Section 4 with this material. But we've done the double slit. We saw how different angles result from different wavelengths. The same thing happens in the diffraction grating, but now there is better separation of the colors, and we have smaller width maxima, so the colors don't overlap as much for the diffraction grating. It's a better instrument for analyzing the different colors of light from some object. We will, however, benefit because the equations we use for the double slit, the d sine theta equals m lambda to locate the maxima, that equation is identical for the diffraction grating. So let's go ahead and take a look at some cases here for the diffraction grating. And here's a photograph. We have thousands of lines per inch. Are not difficult to produce. So a photograph shows the details of these, and any two of these could be considered a double slit. And we've got double, 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 double. And there's a little slight change in the way that the maxima are formed because of this that we'll get to. But just thousands of parallel lines, that's a diffraction grating. And the gratings I'll talk about are gratings where the light passes through the grating. You can also have gratings that are reflection gratings that reflect the light, and we get basically the same effect. So what is the difference between a diffraction grating and a prism? Here's white light coming from the left into both of these devices. The diffraction grating on the top, we get a rainbow of colors. Notice that red is bent the most. It has the greatest angle. And blue, violet, bent the least. The prism, just the opposite occurs. In the prism, the blue light is bent the most and the red light is bent the least. The maxima again are d sine theta equals m lambda. M is an integer and d is the spacing between the slits. They'll all be the same spacing between the slits across the diffraction grating. So we have d sine theta equals m lambda. M is a positive integer, 1, 2, 3. That gives us orders, say, on the top of the sketch. Or m is minus 1, minus 2, minus 3. That would be on the bottom. And this would be order number 1 that they're showing on the slide. So let's keep on progressing. Here shows first order, here's second order. It is true that the first order will be the brightest. The second order will be a little dimmer. If there is a third order, it would be even dimmer. And there's a reason for that as we talk about the single slit diffraction later in this video. So the diffraction grating, evenly spacing between the constant spacing, let's say, between the openings. Small d is still going to characterize that, be our parameter. The light comes through, white light that contains all the colors, and we see the red have the greatest deviation, the purple the smallest deviation from this forward direction, and we'll have white light here in the middle, the central. You might take a look at d sine theta equals m lambda. M is a 0 for the central maximum. Why would the different colors not arrive at different angles at the central maximum? M equals 0. Think about that. Here's a laser beam shining through a diffraction grating. There are not, I don't know if you count across here, 20 or so spots. There are not 20 slits in the diffraction grating. There'd be thousands of slits. The laser light's not going through all of them, but the number of bright spots you see here is not equal to the number of slits in the diffraction grating. They're not equal, not 1 to 1. If there are 10 slits in the diffraction grating, there will be more than 10 dots on the screen. If there are 5 slits in the diffraction grating, there'll be more than 5 dots. And it'll be this, if the distance between the slits is the same, it would be the same pattern on the screen. Or 100 slits will give the same pattern on the screen, basically. Why is only one color present here? Well, you're told this is a laser beam shining through the diffraction grating. The common lasers only have one wavelength that's the major lasing action. So just one wavelength of light coming in. Instead of white light, we'd have all the colors. It'd be a rainbow across the region here. So here's a diagram again showing this extra path length. They call it delta L here. Again, there's a little right triangle between each pair of slits. So that's the d sine theta calculation is delta L, and delta L is going to be m lambda. So you have to imagine, hundreds at least of these slits being involved for the laser beam in creating the spot on the screen. We need delta L to always be, let's say, one wavelength if this is going to be m equal 1 maximum on the screen. So one wavelength, one wavelength, one wavelength, one wavelength, continuing on down. If we would choose an angle slightly different than this theta that produces the maximum, if it would be slightly different, then d sine theta would no longer be one wavelength. It would be off a little bit, and there'd be not as great, not as total constructive interference as there was before. And as we would progress down the slits, the light coming from slits far away would be out of phase with a ray up here, with the light coming from this slit. And consequently, we get destructive interference occurring for the light from, let's say, this slit and the light from 20 slits down the diffraction grating, just guessing at a number. The important concept is that there will be light that's out of phase from this light further down the diffraction grating. There'll be light that's out of phase from this light further down the diffraction grating plus one slit. There'll be light that's out of phase with the light from this slit further down the diffraction grating plus 2. So we'll get out of phase. There's only one specific angle where all these delta L's would be 1 times wavelength, or for the second order 2 times wavelength, and we get a narrower maxima being produced. So here's with the double slit what the intensity of the light looks like at the screen, and here's for the grating, the diffraction grating. The minima is narrower. Again, this is for one color of light. If you'd imagine red, yellow, and blue, so the red here, the blue peak would be separated on this grating from the red peak, and distance would be separated. Up on the double slit, say this is the red again, drawing of its intensity on the screen. The yellow would be just shifted over a little bit. There'd be a lot of overlap between the blue light and the yellow light and the red light. If you imagine 3 of these maxima for the 3 colors, they're going to be overlapping. For the diffraction grating, the separate colors have narrower maxima peaks, and they don't overlap as much. You get better separation of the colors with the diffraction grating. So that's an advantage of the diffraction grating. Also, the separation of colors is better. That's an advantage. Also, for the diffraction grating, the slits tend to be more closely spaced than if someone just creates a double slit. And that gives us a shift that's not shown on this diagram, where the first order maximum would be further to the left at a bigger angle, and that also causes better separation of the colors. If theta is larger, we'll get better separation of the reds, the yellows, and the blues. Iridescence. So we finished the diffraction grating. There's no new formula. D sine theta equals m lambda tells us where the maxima are located. Maybe I should make a comment on the why do they only show m equal 1? Perhaps they show m equals 2. For the diffraction grating, the openings are separated by such a small number that it's easy for the m equals 3 or m equals 4 to create a situation in d sine theta equals m lambda. If we get that back here, d sine theta equals m lambda. If the m is 3 or 4, and we divide by this small number d, the spacing between the slits, we can get in a situation of bigger than 1 on the left, and we can't take inverse sine of that. So it is very common to just have first order and second order visible for the diffraction gratings. A little bit on iridescence, no calculations, just kind of the concepts. you do see some animals and even minerals that'll show sort of enhanced colors, striking colors, iridescent colors. And the Peacock could be one of these. And again, there's interference, constructive interference and destructive interference taking place here. Not identical, they're not built with diffraction gratings in here, but layers of material that give the same effect, the effect of constructive interference for certain wavelengths. So the spacing would kind of control the color that is iridescent, that gives the best constructive interference. So the peacock, butterfly, a mineral called opal. Again, you get this effect of constructive and destructive interference. Certain colors get enhanced. Some beetles here with their shells. View them at different angles. You'll see the colors shift around. Wood nymph, a little bird. Again, vibrant colors produced by constructive interference for that particular color. And a fossil, Ammonite, that again, there's layering in here that causes constructive interference for certain colors, makes them appear brighter. Okay, let's move on to the single slit. Double slits and diffraction gratings are a whole bunch of single slits side by side. It turns out there is a wave effect for the single slit called diffraction. The light does not go straight through into just one beam. Instead, light goes off at various angles to the left and to the right of the opening. And you can see what would be on the screen. There would be spread out central maximum that's much brighter than the other maxima. But there will be a minimum, then a max, then a min, then a max. And again, we have the situation of waves across the wavefront that are effectively being re-emitted, Huygens principle. And we have constructive and destructive interference possible depending on the angle and whether we're off by half a wavelength or a full wavelength or 1.5 wavelengths or 2 full wavelengths will produce minima and maxima. So yes, there is constructive where it's bright, destructive where it's dark, peak and valleys here from waves across the slit are arriving at the same time to produce the valley, the minimum, just as we talked about for the double slit. So here's a little animation, wavefronts coming in, going through, and we get a central maximum, and you can kind of judge for yourself where the minimums are. Some of these aren't real clear, but perhaps a minimum here, a minimum here, a minimum here, minimum out here, and then these are too dark, and it's not realistic. It's a computer simulation. It's good up here, lots of energy in the central maximum, and then we get alternating bright and dark areas on the screen where it's kind of grayed out here. That would be a dark area on the equipment that we use. So there is constructive and destructive interference. Even though there's only one opening, the wave interferes with itself as it progresses through that opening. The slide tells you what's going on here. We'll use capital D for the width of the opening in our equation that's about to come up. All the energy does not fall in one spot straight ahead of the opening. We do have a central max. It's a lot brighter than the other maxima. We have central max, a first minimum, a first order maximum, minimum, maximum, alternating across the screen. So light coming through straight ahead produces a central max. When we go off center, and there's a situation, and I guess I would prefer to talk about this, just this drawing up here. So let's take a ray from the very top of the opening and a ray in the middle. Let that energy go out to the screen. That's a long way away. These lines will meet out at the screen. Well, this is, say you have a peak at the opening here. There would be a valley here, a peak all the way across the opening, but half wavelength out towards our spot on the screen. This will be a valley now at this dotted line that comes across here. So I have a peak and a valley for these two, that's going to cancel. There's going to be a peak and a valley for these two, that's going to cancel. There's a peak and a valley for these two, that's going to cancel. That's going to produce a minimum on the screen. There's only one equation for the single slit. That's where the minima are located. So there's capital D, the size of the opening. Need to put that in meters. sine of theta that we'll calculate, and then again the m is an integer, but now we start at 1 instead of 0. For the double slit, we start the list of integers at 1, and 1, 2, 3, 4, or minus 1, minus 2, minus 3, minus 4 would be our values. But this locates the angle where the minimum occurs, and then the y position on the screen, again, tangent theta equals y over L. Same formula as we used for the double slit. So here's yellow light shining through two slits. Each of the two slits is a single slit. The double slit pattern is producing these alternating bright and dark bands here, constructive and destructive interference. Down here, constructive and destructive interference. Why do the maxima get dimmer to the left and the right? You know, d sine theta equals m lambda. That tells you nothing about the intensity of the light. And why are some of the maxima missing? So we're getting a little dimmer here, and then the double slit equation would predict a maximum at this location, would also predict a maximum up here that we're not seeing. Why are we missing some maxima? Double slit would predict a bright band here, would predict a bright band out here, so forth and so on, to the left and to the right. Why are we missing some light from what the double slit equation predicts? Well, here's the intensity of the single slit pattern. What if the double slit pattern predicts a maximum at this location where the single slit pattern predicts a minimum? Remember, in the double slit, each of the two slits is a single slit. So at an angle from the slit mechanism that would say I'm going to have a maximum here, the double slit pattern. At that angle, the same angle for both of the two slits, the single slit equation predicts a minimum. Well, we do have constructive interference on the screen in the double slit pattern, but it's 0 plus 0. Each single slit sends out 0 energy at this particular angle. You know, sine of theta is being plotted across here. You take inverse sine to get the theta value. But each single slit is sending out 0 energy in this direction. That arrives at the screen, and the double slit equation says add them together constructively. You add 0 and 0, and you end up with no light. This is called a missing order. So where the single slit pattern predicts a 0 intensity, and the double slit pattern predicts as constructive interference, a bright spot, the single slit pattern wins, because it's 0 plus 0 that's being added up. So in this slide, if you notice, the dark spots are at the same spot. So the slit width is the same for both of these, but the interference pattern a little narrower down here. So there's a different separation of the two slits. So single slit pattern predicts a 0 at this location, at this angle. The double slit pattern predicts a maximum. The single slit pattern wins, you know, by observation and by logic. 0 plus 0 is still 0. So that's a missing order, where the single slit pattern predicts a 0, the double slit pattern predicts a maximum. That order predicted by the double slit pattern would be missing order. So that's the end of day 2 of wave optics. A diffraction grating is not difficult. It's just multiple double slits side by side. It does have an advantage in that the maxima for a particular color are narrower, and helps us to study the light better because the colors don't overlap. And also the colors are spread out to bigger angles because the spacing between the slits is usually smaller than what you do with a single double slit system. Iridescence, a little fun in nature, animals viewing vibrant colors. Again, constructive interference is taking place there. And constructive interference and destructive takes place even if we only have one opening. The light wave interferes with itself as it comes through the single slit. And the single slit pattern is the most important. It controls the overall brightness on the screen. That's why the light dims down as we move away from the central maximum. Oh, keep reading, ask your instructor some questions, work some sample problems on your own.